Okay, I make that 2 o'clock, so perhaps we should make a start on this afternoon session. So welcome back, or if you haven't been already, then welcome. The first speaker today is, the first speaker of this afternoon is Stig Venus from Uninet, and he will be discussing the work of the M6 bone. This talk is entitled International Experiments with IP version 6.
Yeah, thanks. So I will tell you a bit about a project called M6 bone, which is a large-scale deployment of IPv6 multicast, and also something about what's going on with 6net and multicast and some of the issues we have found with multicast for IPv6. So yeah, let's start. So yeah, this is more or less what I will say. Also say something about some reflectors and a gateway that will act as sort of a translation device between IPv4 and IPv6 multicast, and something about available applications and content. So M6 bone, that was established in July 2001 by some organizations in France. Reflectors is the French NRN. Today there's about 40 countries or 40 sites connected from 4 different continents, so it's getting pretty large. The goals are to give people that want to play with multicast connectivity, test some software and hardware with IPv6 multicast, try to see how well it works, find what the issues are, and also to actually use it for something useful, like having some conferences. There's some contact info at the bottom here. There's a website and a mail address you can reach the M6 bone team on, and there's also a mailing list. So I guess you can look you can find a presentation someplace else if you are interested in writing them down. So this is what the M6 bone looks like from sort of the world perspective. The sort of hub is in France, and from there are tunnels out to the US and Korea, Philippines, Senegal in Africa. It's getting large. And in Europe, it looks more or less like this. There are some details that are hidden in these clouds. There's a lot of tunnels around the world, around Europe. There's not that many routers yet supporting IPv6 multicast, so in most cases these are tunnels that are going over either IP4 or maybe also IPv6 between the different routers that are actually supported. So a bit about the technology itself. PIM sparse mode is being used. There are multiple RPs. There's one global RP that is operated by Reflectors. I will explain a bit about inter-domain multicast later and why it's a little bit problematic. So the solution right now is to use just one global RP for all of the entire network. It may not scale in the end, but it works fine for the tests at least. BSR is used for distributing the RP config in most cases. And RIP is being used for in the routing, more or less. And there's some tunnels to avoid or go around the routers that don't support multicast. These tunnels are only used for multicast. We don't want all the IP6 traffic to go through this tunnel network. There's some problems with at least some of the routers used that they can't separate unicast and multicast. You always use the normal routing table for both, the unicast routing table for also doing the RPF checks and so on for multicast. So the solution being done then is that we actually, in most cases, have separate routers for unicast and multicast. And then you can just make the unicast table on the multicast router look like what you want the multicast, or yeah, where you want the multicast to go. If you, yeah, hope you see what I mean. The routers used are, until recently it's been mostly PCs running FreeBSD or different BSD variants with CAMA, but there are also some Cisco implementation available on EFT, and 6-win and Hitachi routers are also being tested. Maybe some others, but these are the ones I'm aware of. And there's a lot of different hosts being used, mostly BSD, Linux, and XP, I think. There are some of the routers that doesn't support BSR yet, so they are configured manually, and there are also some routes being exchanged with other things than RIP and G, but this is sort of the normal or common case. The 6-net network, I'll tell you a bit what's going on here. So this is, well, more or less what the normal 6-net network looks like, and a few days ago these routers in the core, well, most of the ones you see there, were upgraded to support IP6 multicast. And we have now started the first tests, and the idea is to have native multicast all over 6-net in, well, hopefully a few weeks, or I'd say a few months, but so far it looks promising. There's been quite a lot of 6-net partners connected already to the M6 phone, but they have been doing this directly with tunnels to the rest of the M6 phone. What they want to do now is, as I said, to have native multicast in 6-net and connect the entire 6-net as sort of one network to the M6 phone. And we also want to have a zone or a smaller scope, not global scope, being used in 6-net, so it can sort of limit some traffic to only be in 6-net. And we also then need to have an RP for a smaller scope in 6-net that won't be visible outside 6-net. But we will still use this one single global RP outside 6-net for global traffic. We need to do this currently if we want to have multicast together with people outside 6-net. I'm coming back to that. And in 6-net we are using mostly Cisco routers, and they actually now support multicast routes, so you can have unicast and multicast going different ways. If you're lucky, running native multicast all over, you can have the same topology for both unicast and multicast, and that's of course the best, but it's not that easy to actually achieve yet, since a lot of routers don't support it. And between the Ciscos, we're also using MPGP for exchanging the routes. Okay, then about inter-domain multicast. As we heard earlier today, there's nothing like MSDP to sort of exchange knowledge about sources between RPs, and that means that you can't have, say, two different RPs, two different places in the network for, let's say global scope, or for one single group for that matter, because the people that are joining or sending to one of the RPs won't have connectivity to the other people that are using the other RP. So in effect, for a given group, you need to have a single RP if people are to have connectivity. So that's why we use this one single global RP. So in effect, we might never see global IP6 multicast as we have it for IPv4 today, because it can be very hard to find someone willing to operate an RP for, say, all global scope or for some global group, and there might be other providers that don't want to trust the other provider to do it, and so on. So not so sure it will work out. And then we also have a problem with services like SDR using SAP to announce active sources or sessions being available, because it actually relies on having one single group where everyone around the world can join the group and receive whatever announcements the others send. So you might have to come up with some other solution. Yeah, of course you could consider asking someone nicely to set up an RP for just serving the SAP group around the world, but there's the matter of trust and so on as well. But there are some alternatives or some, well, solutions that at least give us some sort of multicast service. I'm going to talk about those now. So it's SSM and embedded RP. SSM or source-specific multicast, that's available for IPv4 as well, but it's not really deployed, and well, not yet for IPv6 either, but implementations are getting there, and I think this might happen. And this is quite good for, say, broadcasting, where you actually just want one single source. It solves one of the problems you had with multicast until now with security and so on, where some TV channel don't want someone else to suddenly start sending on the same address. So that solves one problem, and SSM can easily be used globally because there's no rendezvous points or anything like that. You just need to have multicast enabled in all the routers on the path from the source to the, from the receiver to the source. But for, say, video conferencing, SSM is much more complex because you might have several participants coming and going, and you need to actually know about every source, every participant, because you need to explicitly join each of them. So if you want to do this, you would need the application to somehow keep track of who is available and somehow distribute info about sources and so on. There are some ways of doing it, but what happens is that you in practice takes the complexity that the RPs and MSDPs solve today and sort of push that up to the application level. It might be a good thing, but it also makes the applications more complex. The other solution is embedded RP. The idea here is that you can somehow, in the address of a multicast group, embed or specify the address of the rendezvous point to use for that group. So when someone's from the web or from some announcements, whatever, learns about the multicast group, they can just join that group, and the routers will immediately know which RP to join. There's no special configuration necessary of the routers. And this could work on a global scale, and and it's ASM, the normal multicast model. But it doesn't really solve all the problems because it's still just one single RP per group. You actually encode the address of the RP in the group address, so that's pretty obvious. But you can at least imagine that someone, if someone wants to create a video conference, for instance, they just pick their own RP and they generate a group address containing their own RP address and announce them to other participants, and they can all join, and everything will work as it is today. The only problem is that the RP will be, they will all use the same RP, but I think that's okay. Main problem is perhaps if you have some sessions where there's no real owner of the session, like SAP, for instance, or if you have some sort of peer-to-peer application or whatever using multicast, where you just have individual people starting and stopping their application, and there's really no one sort of owning any special group addresses or rendezvous points. But it's an interesting solution, and it's not something you can do with IPv4 since you don't have space enough to encode any addresses. Yeah, okay. Then I'll go on to things that more at the application level and some sort of transition tools, if you like. One thing is reflectors. That's been around for a long time for IPv4. The idea is that you can give access to multicast content to people that don't have a multicast. You can have a device that joins a multicast group and sends it out as unicast to different unicast participants. And this can be quite useful, at least if there's not too many recipients and it's placed close to the people receiving. And yeah, they can also be two-way, where actually people can send unicast to the reflector and it goes out to all the other participants and to the multicast group. And yeah, this is especially useful now when you are doing both IPv4 and IPv6, because you could have, say, an IPv4 group, IPv4 multicast, and then have unicast participants using both IPv4 or IPv6. Or you can have an IP6 group with IPv4 and IP6 recipients, or yeah, whatever. You can have different combinations of IPv4 and IPv6, and they can actually work together. And we also have a sort of reflector that actually just joins an IP4 group and an IP6 group at the same time, and sort of takes all the traffic from one side and send it out on the other side, and that's also quite useful. So this is a way of sort of gluing together people that got unicast and multicast and IP4 and IP6, and you actually had some video conferencing with people using all these 4 combinations together in one single conference. It worked quite well. This is some reflector that we have been testing in 6net. I'm going to talk a little bit about that. It's completely free and available at this URL. Okay, I'll say a bit about that. For each group that you want to reflect, you need to start a new reflector process. And as soon as you start the reflector, it will join the group even if there's no recipients, which is not so good perhaps, but well. But what's really special and nice about these reflectors is that if you have applications using RTP, RTCP, for instance, they will actually start sending even if they don't receive anything. And as soon as someone starts, for instance, Wik or some other tool with RTP and the unicast address of the reflector, it will start sending reports that it doesn't receive anything. And then the reflector will know that the application is there and can start streaming or reflecting from multicast to that unicast address of the client. So the user just starts his application as normal, and the reflector will automatically see that it's there, which is quite nice, I think. Only problem is, of course, that you have some applications that doesn't send until they receive, or they don't send at all. They just want to passively receive data. Then you could have some other solution using web or send email to an administrator or whatever to sort of ask for some unicast traffic, but that's not so nice. And they can actually also stop sending when the user quits or closes the application, because with RTP, RTCP, the application will all the time send reports that it's receiving such and such, and when the application dies, the reflector will see that, oh, there's no more reports, then it's gone, and it can stop sending unicast. So I think it's quite nice, but there are some problems, like, for instance, you have to start one process for a group, so it's okay to do it for a few specific groups, but you can't really use it to give access to all of IP4 multicast into IPv6. You can't start this for all possible IP4 multicast addresses. So that's why I've been working on a multicast gateway where I actually want to do this. You should be able to easily reach all of IP4 multicast from IPv6, I think, and also the other direction if possible. And that's what I'm trying to do here. So this solution, well, it's described in this draft if you want to see more how it is in technical detail. But it translates between IP4 and IP6 multicast, and it can be placed, for instance, at the border between an IP4 and IP6 only network. And it's using PIM sparse mode. It can actually be used without changing any other things in the network. I'll explain why later. So it's quite easy to deploy, I think. And the main idea is that we embed all of IP4 multicast into IPv6. So we have 1/96 IP6 multicast prefix, and at the end you added 32 bits of the IP4 address. And yeah, when you're using this gateway, you will more or less join together IP4 and IP6 multicast distribution trees, where sort of the IP6 tree is glued onto the end or edge of the IP4 tree, but well, I'll tell you a bit more about that. And yeah, the gateway is an IP4 leaf node that just joins as normal IP4 host or sends. But what's special is that the gateway is a rendezvous point for the /96 prefix in IPv6. And that's really what makes it work, because as a rendezvous point, it will know about all the sources and senders for these groups. And yeah, this is what a user sees. You can receive data from an IP4 group, ABCD, by joining the corresponding IP6 group, this prefix, and then ABCD at the end. And you can also send to an IP4 group by sending to this IP6 group. And yeah, you can also send without joining. And it's perfectly possible to have some video conference with IP4 and IP6 participants at the same time using this gateway. You have full, yeah, the traffic passes both ways through the gateway from both IP4 and IP6 sides, so it's full duplex route, I should say. So yeah, okay, I already told you this. It's a host on the IP4 side and rendezvous point on the IP6 side. And yeah, this shows a little bit how it works. When the yeah, you have some IP6 host joining. Let's see. Oh, here an IP6 host that joins this multicast group up here. Actually, that has embedded this address we see up here at the end. And you are actually also able to write IP6 addresses like this, if you like, with an IP4 address at the end. That's perfectly acceptable, or it's allowed. So in that way, you can easily see which group it actually refers to. So the host sends to, in this case, joins this address. The joins are going up to the gateway. Gateway will look at this last 32 bits and say that it's this group that someone wants to join. Then the gateway joins this group as a normal host, and any data it receives from that IP4 group or to that group will then be sent down to the hosts down here. And everything happening up here is a normal PIM sparse mode, except what's being done in the gateway. Okay, right. I think I was using the wrong slide, but it's not so important. This is the one for joining. Yeah, that's what I explained. Well, this is actually for sending. The sending also works as usual, except that in this case, what that's happening on a lot of multicast routers anyway, is that the gateway will always join. When it receives register packets, it will always join, because it knows that it needs to get all the data to resend it, and it's not efficient to use register. Well, okay. Yeah, you can read all the details in the draft, or ask me if you want to know more about it. Okay, and then applications. Especially wanted to show you this because it's a pretty large tested weekend rat we have done in 6net. Actually, there's also some people outside 6net here, so maybe I should say M6 bound. What's special here is that you have actually some people using IP4 and some using IPv6. If you see up here, for instance, I know it's hard to see, but there's an IP6 address up there, while here there is an IP4 address. Here's also another IP4 address. Most of them are IP6. So you have people using both 4 and 6 together in the same conference or session. This is a pretty large session, I think. So, well. Yeah, this is my last slide. There's not that many applications available yet, but there's the usual M-bound tools. There's some patches for different things, FreeAmp, for instance. There's MIM, or MIM, to receive MPEG-1 and MP3. Some tools like TTCP and iPerf. There's also a multicast beacon that we also are running in 6net to see how well or how badly things are going. But, well, and this beacon is perhaps a bit interesting because it was more or less written for IPv4. No one thought about IPv6. But it's written in Java, and since Java sort of manages to have an abstract view to the sort of IP addresses, or what I should say, it works just fine with IPv6, even though it wasn't thought about. You just sort of insert an IPv6 address instead of an IPv4 address. For content, we have some different sessions going on with Vic and Rat. People sending some view out their office window or whatever. But we also try to have some active sessions, some video conferences. There's a sort of radio available with some music you can listen to using FreeAmp, for instance. There's also some Norwegian national broadcasting radio channels. As long as this is sort of experimental network and for testing, it should be fine. And all IP4 multicast sessions should be available using this gateway. The gateway is actually deployed today on the M6 phone. So if you join the M6 phone, you will also actually be able to use the gateway. The only problem, of course, is that there's a lot of applications that haven't been ported to IPv6. So even though you can join the group and receive the data and so on, you may not be able to do anything with it. But that's coming, I hope. So, yeah. Then I have some questions, I hope.
Why is there no equivalent to MSDP?
I think most people agree that MSDP is a bit ugly and doesn't scale and should only be a short-term solution. And it's never really been accepted, but it's still being used for IPv4. Some people would like it for IPv6, but the general view in the IETF is that we don't want it. It might, so I think there's a general view that SSM might be enough. At least one wants to try that. And if it comes to, if in a few years it's clear that you need something more, then I think people would work harder on finding some solution again. Let me just say that I really hope some of you want to join this experiment, and feel free to contact me or the addresses I posted there if you have any questions or want to know more about it. It's not so difficult to start testing, actually. Okay.
Try again. Okay, thank you, Stig. With that, we'll move on to our next presentation. We've heard a lot already about the various uses and applications of IPv6, but obviously, as it's used more and more widely, you run into a number of issues with regards to security. So the next presentation is by Eric Marin, who will discuss some of these issues and some of the things that we need to consider. His talk is entitled, "What are the new challenges of securing IPv6 networks?"
So while he's loading the presentation, so good afternoon. I'm working at Cisco, focusing on security technologies. So usually IPv4 security technologies. I don't think it's this one. Well, I will have a hard time doing this presentation anyway. So IPv4 security technologies, that means intrusion detection, IPsec, firewalling, all those type of things. I think that's this one. Yeah. So I started to look at the IPv6 security issues about 18 months. Yeah, thank you. About 18 months ago, and obviously thank you. Obviously, in 30 minutes, there's no way I can pretend to address all the security issues in IPv6. Imagine if I had the same session on IPv4 and security, probably a week would barely be enough to address all the issues. So my humble objective and goal here is more to raise awareness on some of the IPv6 aspects where security should be really taken into consideration. In the way IPv6 has been defined and in the way IPv6 is being used. So when I started to look at, and again, it's only about 18 months that I started to really look at IPv6. So I don't pretend to be the IPv6 guru, not for sure. This is for sure. But when I started to look at the different drafts and how security was addressed in IPv6, almost in every security section in all drafts, it was always mentioned, and for the security consideration, please have a look at IPsec. The fact is that IPsec has been used for years already in IPv4. So we know how it works. We know what kind of issues it can solve. But we also know when it doesn't really work because it doesn't scale or because it's very hard to manage and to deploy. So IPsec is definitely not the answer for every security aspect of IPv6. And frankly speaking, when for the last 6 to 9 months, I saw a big change in the way the different drafts and proposals are addressing the security issues in IPv6. So it really looks like the awareness is there now, and IPsec is not the only answer to all security aspects in V6, which is good. So again. This is basically a slide that we know from IPv4 already. One of the big issues, and we should talk about it later when I'm going to talk about mobile IP, V6, and security. One of the main issues is because of IPv6, we are potentially talking about millions of devices. And when you really want to deploy IPsec in a scalable manner, for millions of devices, you need what we call a PKI, a public key infrastructure. And we know from IPv4 that deploying and using a PKI is not an easy thing to do. Although it's the best secured way to deploy IPsec, it's not always feasible because it's difficult to manage, it's expensive, it requires lots of dedicated stuff. So PKI usually is the barrier. So this is the agenda, and again, there are some things that I decided to not to talk about this afternoon. So I will first talk about things that, in the first section, I'd like to do a parallel of things that we knew from IPv4 and how they are tackled in IPv6. So I will do this kind of parallel. Then I'll talk about the challenge of filtering IPv6 packets, because this is much more difficult, I would say, in IPv6 now. I also would like to talk about fragmentation, and I'll explain why I'm going to talk about fragmentation in an IPv6, in a security talk later. And then in the conclusion, I also like to touch upon things like mobile IPv6, security in the transition mechanisms as well, which is an important aspect of it. So in IPv6, there are a few things that I think we can make a parallel with IPv4 too. Is auto configuration, ICMP-v6, which is obviously used a lot in a campus or on the internal network, and duplicate address detection, which also is based on ICMP. And we'll see that that here there is a big lack of security. And I believe that this morning Harald briefly touched upon this type of protocols and the lack of security. So this is what I'd like to talk about very briefly. So stateless auto-configuration, this is just one slide that I am reusing. But again, it's all based on ICMP. And to protect it, the answer is, use AH, which is one of the IPsec protocol. Use AH to ensure integrity for that packet. Well, again, that's the same problem that I described earlier. Because to deploy IPsec, you need to have some bootstrap configuration already in place. And if you need to basically to build a trust relationship between all the devices that you want to be part of your trust domain. And this requires some configuration. So one of the answer is, because AH and IPsec obviously can't really be deployed for hundreds or millions of devices here on the network, or it's going to be very, very difficult to manage. But potential solution would be something equivalent to 802.1x that we have at layer 2 in IPv4. Neighbor discovery, same thing here. Neighbor discovery and neighbor solicitation. Here it's same issue, based on ICMP-v6, and I think it's mentioned in one of the next slides, but it's really like ARP in IPv4. And we know that there's no security mechanisms built in ARP for IPv4. So that's exactly the same thing here. And actually, very few people are really paying attention to layer 2 security, to their security in their switching environment because of ARP. So this is going to be the same thing. And for that, there is also different ways by if you're on the network already, by crafting special packets to DOS a host by preventing him from getting an IP address. So those three examples here are really all about the same thing, which is, and that's why I went very briefly through these 3 slides. But it's really about ARP-like security in v4, which has non-security at all. And again, be aware of those issues. Be aware. You're probably aware already of it, but that's one of the things I really would like to emphasize, is that there's no mechanisms in place. There is one working group that also Harald mentioned this morning, which is addressing this, which is the SEND, S-E-N-D working group. But so far as I can tell, there's no deployable proposal. For the time being, all the issues have been properly listed and addressed, but now it's time to think about some security mechanisms now. Also, a different aspect of IPv6 is the IPv6 routing header, which is heavily used not only in mobile IP, but in many other aspects of IPv6. And this is simply a chart that explains how the routing header is being used when traversing a network from A to D. And basically, the routing header contains the list of intermediate routers we want the packet to go through. So this is fine. It's actually very close to loose source routing we have in IPv4. But the issue here, and it's actually mentioned in a very, very good and very readable draft, which I mentioned here at the bottom, which addresses the issues of routing header security and home address security. which are very, very closely related. The issue here with routing header is that you have the ability to insert the destination IP address of your victim, basically. But this will go unnoticed by some check or filtering devices that you may have, because a simple filtering devices will simply say source IP address, a spoofed IP address from an attacker, destination IP address that could be a web server, a host on the network that would be used as a reflector, because the final victim's IP address is going to be in the routing header. So here there are some issues in how we can filter the routing headers. So this is very well explained in this draft. And again, my objective here is not to go into the details of those things, but more to raise awareness. But routing header is very challenging for security in IPv6. So one possibility would be, and I'm going to talk about filtering IPv6 packets. So you could have the ability to filter on packets that have routing header present in the packet. That would work for sure, because here you don't have you filter everything or you block everything. But routing header is heavily used in mobile IP. So if you're really sure that you don't have any mobile IPv6 devices or in your network, then you could probably filter based on the routing header itself. But again, you have to be sure that mobile IPv6 is not used in your network. Again, if you're interested in the issues of security and IPv6, I really recommend this draft because it's very well explained. I'm not mentioning home address, but it would be the same issue. Instead of playing with the destination IP address, home address allows you to change the source IP address in the packet, basically. So filtering IPv6, I wanted to mention that because filtering IPv6 does present some serious challenges from IPv4. So here I just mentioned for references or as an example, standard ACL in iOS and extended ACL since 12.280. And filtering on IPv6 packets, as I said, is challenging. The reason why it's challenging is that instead of simply looking at your source IP address and port layer 4 information, here you have to scan through all your packets, all your different daisy chain headers to extract the proper information you will filter on. So I'll come back to the fragmentation issue later on, but generally speaking, this is an issue when filtering on IPv6 packets. You need to extract the info, and this is obviously a bit more difficult. So filtering extension headers, as I mentioned, does require this process of going through the whole packet. So these are simply examples of extension headers you have in an IPv6 packet, but there are plenty others. And again, I shall come back to the fragmentation issues, but this is definitely a challenge. So this is an example of what kind of details on what kind of fields or extension headers we can filter on using extended ACL. So you see that obviously we can filter on the upper layer protocol. So that would be UDP, TCP, or ICMP, like any standard IPv4 ACL. SYN, ACK, FIN, etc., etc. The difference here is that we have the ability to filter on also IPv6 header options. So that's where you would use, that's this option that you have in extended ACL that you would use to filter on packets that have routing headers present. From what I said already, if you don't have mobile IPv6 nodes on your network and you want to filter routing headers that would be the type of extended ACL you would use in your network. So very briefly on in one slide, although it's only an example, but there are many other reasons why IPv6 filtering is a bit more difficult. So filtering 2827 becomes more difficult, and the reason, generally speaking, is simply because you have to handle many more IP addresses on a network. Because simply a node can have much more IPv6 addresses that it used to have with IPv4. And this obviously, when doing filtering, is a concern. Renumbering, same thing. For a period of time, you may have to deal with different type of subnet or different type of IP addresses. So again, when defining ACL and filtering at the edge, this is also something which becomes more challenging, obviously. So I wanted also to, because this is something which is not very well known by people in general, from my perspective, by Cisco customers I'm talking to. It was not very well known in IPv4, although it exists for years, and it's definitely not very well known in IPv6 at all. And I do believe it does, because obviously we are looking at a fully stateful based firewall. But if you want to do some form of stateful filtering already, the reflexive ACL is the solution for the time being. A reflexive ACL is a normal ACL, but when you specify, so in iOS, it's the name is reflexive, or reflect. But basically what it says is based on an incoming packet that will hit this reflexive ACL, it means that automatically a mirrored ACL will be added dynamically in your router. So a mirrored ACL simply means that you invert source and destination addresses as well as ports. So, and this mirrored ACL will stay here for the duration of the connection. So for the duration of the connection, you will maintain a kind of state in your router for both direction, incoming and outgoing packets, that will have to match this ACL. So I think it's a pretty powerful tool to already in IPv6 do some form of filtering. Because I've been trying to, not hacking, but I've been trying to visit some sites, some IPv6 websites or networks. And usually when you use some tools, some scanning tools that I'm going to talk about at the end, using IPv4 on those sites, usually it's pretty, I mean, you see that either you have a firewall Okay. So when visiting these sites, you can very easily see that IPv4 usually is taken into consideration from the security perspective. But IPv6 is still yet, usually IPv6 packets go unfiltered. And it's very easy to actually circumvent some IPv4 security measures using IPv6. So that's why I'm saying that filtering is definitely, filtering IPv6 packets really should be taken into consideration, because it's not done, I would not say it's not done at all for the time being, but it's, people are not paying enough attention to those kind of security measures. That's been my experience. I don't know if it's been yours. So I wanted to talk about fragmentation as well. Reason I included fragmentation in a security presentation, it's because fragmented packets are in IPv4, so I do expect the same in IPv6. Fragmented packets are very heavily used by hackers. or attackers. You have many tools freely available, as usual, that tries to forge attacking packets, but instead of simply sending these packets, usually those tools will fragment these packets and put them in a different order. By doing so, you want to do two things. You want to, if possible, try to pass some ACL check or filtering, and also you want to evade from some intrusion detection tool that, because this basically makes IDS job much more difficult. So fragmented packets are very heavily used, as I said, by malicious persons. So this is the fragment header IPv6. So in IPv4, very quickly, in IPv4, when you do specify, it's very easy to distinguish a fragment and to extract the necessary information from the first fragment, of the packet. Because in IPv4, you have enough information in this first fragment to do filtering on. Enough information means you have the ability from the first fragment to extract source, destination addresses, as well as ports, and you can decide what to do on this first fragment. So basically, the ability to define a fragment keyword in an ACL is used to filter fragments, and this is to prevent some form of denial of service attacks, because you have the ability to do something about fragments, either completely filter them or rate limit fragments, for example. So this is used mainly against DOS, but it's very easy to extract this information in v4. In IPv6, again, same issue. To extract the same type of information, you have to scan through all the extensions headers that are potentially present in your daisy chain of headers. So you may not be able to extract the same type of information from your first fragment. So this, as I indicated here at the bottom, this makes matching against the first fragment very non-deterministic. So you have to deal with the fragments differently in IPv6. So that's the reason why in the fragment keyword has a different meaning when defining a fragment in an ACL. This new meaning in IPv6, when you try to identify a fragment, to filter those fragments, means that you will match all non-initial fragments, as in v4, and the first fragment if the protocol cannot be determined. So this is a new behavior in iOS, but it's not only iOS related. That's because of the way an IPv6 packet is formed. And as a matter of fact, this is for information. There's a new keyword which is undetermined transport that will catch packets where we cannot determine the protocols and all the information I was talking about. So again, I just wanted to raise awareness on this new behavior because dealing with fragmentation is an important aspect, in my opinion, when dealing with security. And again, this is based purely on experiences or feedback from the IPv4 world, but I don't see any reason why hackers would not use fragments in IPv6. So in conclusion, so it's a long conclusion because I wanted to talk about two different things as well before really making a short conclusion. Two areas also where I do believe security needs to be seriously looked at in IPv6. The first one is mobile IP. It's been mentioned this morning during this morning sessions. The issue with mobile IP is mobile IP in IPv6, making use of home address and routing headers, is that you have the ability to avoid the famous triangle by establishing a direct communication using binding updates. Now the whole issue is about securing those binding updates, because you want to establish a trust relationship again with someone you want to properly authenticate. And for a long time in the mobile IPv6 draft or proposal, it was always mentioned that for securing those binding updates, you had to use AH, that is IPsec. But again, with mobile IP, I'm pretty sure we can one day envision to have thousands, millions of devices, right, using IPv6. And we are still back to the problem I described earlier, that is public infrastructure, or that is establishing a trust relationship between nodes. And to establish a trust relationship between two nodes, they need to share a common secret or a common piece of information for establishing that trust in their domain. So for mobile IP, that's a big issue. And there are many work being done currently at the IETF about this same issue of securing binding updates or securing mobile IPv6. About 6 months or 9 months ago, I believe it was in the version, if I recall properly, in version 18 of the draft, some security check have been added in mobile IPv6, which is a good thing. And it's called the return routability test. That basically, in a nutshell, it's the exchange of few cookies between two nodes that are going to be exchanged to add some security before sending a binding update between two nodes. But it's not as secure as AH. It does not provide all the levels of security that you may have with IPsec, but it's some form of security check, if you will. And at least this is being worked on and considered at the IETF. But this is an area where lots of work is being put. Transition mechanism. So sorry if I put so many things in one slide, but it's a very interesting area as well. And here I mentioned two things that are very close anyway, that I've been reading very recently. The first one is a deliverable on the 6net.org, so you may have seen it already, but it's a very good document that is also very close to this draft that will list all the issues of 624, of the security of issues of a 624, automatic 624 tunnel. Oh, so what I did put here is actually extract from this draft. Even though there's most of the things here are pure ACL checking, I mean, things that we do usually, but in that draft, they are properly identified and listed. So one of the things in 624, automatic 624, is, for example, the whole challenge of 624 security is to make sure that someone doesn't have the ability to establish a 64 tunnel to another router or to a 64 relay. So we want to make some check here before accepting this tunnel. So I would, since transition mechanisms are obviously heavily used and are going to be heavily used for some time, I do encourage people that are interested in that subject to have a look at it. Also, one thing which I've never really seen deployed for the few people I've been working on are the use of IPsec protecting those tunnels. And this is something we can actually do, for example, in iOS, where you have the ability to add IPsec on top of a manually v6 in v4 manually configured v6 in v4 tunnels. And this is something you could that could be deployed. I think it's a very nice and easy way to add security to a tunnel. So again, that should be also considered when possible. And finally, although I think I mentioned most of the points, so I touch upon most of the points during this short introduction. Again, IPsec is not the answer to every IPv6 security issue. And even though I try to list some of the things where I do believe we should really pay attention in IPv6 with regard to security, but there are going to be many new areas where works are going to be done. And I've listed for your information, because when we look at security, we always look at it from the defense perspective, if I could put it that way. But it's also always interested to try to see what is available on the internet, or are the tools that allows you to forge and craft malicious packets. Are those tools already IPv6 aware? And here I've listed a few tools, and I did this research about 2-3 weeks ago, and I was personally amazed by the number of tools that are already IPv6 capable. Although most of the time they are IPv6 aware or capable in some very basic shape, but still, this really proves that in 6 or 12 months from now, all those tools are going to be fully IPv6 capable. That is, for someone trying to getting into a network, they would have the ability to use any of those tools to forge packets. And this is from the other side. But there are also some IPv6 tools that are also developed. This is mostly on Linux and BSD. That's for your information. And last slide. This was posted on a mailing list by Lance Spitzner. So for those working in security, Lance is someone who is pretty well known, and he's been working for the last 2 years on a project which is called Honeypot. And again, honeypot is the concept of an honeypot in the security area is for a potential victim to build a completely separated network to attract hackers. And so you know that you don't have anything really critical or operational on this network, but your goal is to attract hackers. And so you know that they will go after the servers or the machines that you have on this separated network. But then you really look at what is going on this network. You analyze the logs, and you learn from what the hackers are trying to do on your network. So he's been doing that, and if you have time to read the quote while I was speaking, basically a new form of evasion technique is to build a tunnel, so an IPv4 in IPv6 tunnel, so that IDS or filtering devices don't have the ability to look at the original IPv4 packets. So using tunneling mechanisms, you have the ability to evade IDS or filtering device. So this was my last slide. And again, I just wanted to, because when working on IPv6, all the things that mostly we are more concerned with the connectivity itself. While learning from IPv4, I do believe that we should take security into consideration from day one when deploying the connectivity, and it should not be an afterthought process as it used to be in IPv4. So I believe we should learn from that. And I'm done. So if you have any questions.
Okay, I have just a maybe two comments. First is, I think that the fragmentation is a non-issue in IPv6, basically, since it should not appear in most cases. The end stations are supposed to do MTU discovery, so the usage of the fragmentation router should be really rare, and so normally you would just filter out packets with fragmentation header. And my second comment is that I really think that most IPv6 network use some tunneling, manually configured tunnel. So in my opinion, this is the single most important vulnerability in most IPv6 network, except of 6net, of course. But really, there are many tunnel-based attacks which are easy to do in most IPv6 networks.
For fragment, sorry, I wanted to wake up everyone. For fragmentation, I agree, but you still have the ability to craft fragmented packets. That was my point. For transition mechanisms, I fully agree. Since it's going to be the mechanisms that are going to be used for the next, I don't know, 1, 2, 3, 4, 5 years. That's why I mentioned at the end those draft and document, because this is one of the area where I think we should really look at from the security perspective. So that's what I mentioned. I think securing those tunnels with IPsec should be. I don't think any problem in doing that. I agree. Thanks.
One comment about Lada's comment that when you measure the number of fragmented packets, you usually don't see any in a real working IPv6 environment. So probably you can quite strict on such a filtering. I have a question. Do you think that really the firewall is the solution for IPv6? Because firewall is somehow, it's putting the dead horse in another route and not solving the problem of the host security problem.
Frankly speaking, I don't have the answer. Let's be honest. It's a good point. I think you would need a firewall in many cases anyway. Using those transition mechanisms, you probably need a firewall at, for example, where you terminate those tunnels, for example, at the edge. Yeah. But since you'll have many nodes, then you need some form of distributed security anyway. And I know that some work has been started. Some people are trying to form a group or to start this work. I think it's going to be a pretty interesting work. But I believe that more and more security also should be put on the nodes itself. Whether they should handle routing headers, for example, those kind of headers. But to answer your question, yes, firewall will be needed, but other things will need to be done, especially at the node. And if you need to manage security on millions of nodes, then you need a way to do that. And it's still something which needs to be solved, definitely. Sorry.
Again, a comment regarding the using IPsec for securing tunnels, IPv4 tunnels. Do you think that it's a real solution? Because usually the IPsec has such an overhead that you want to avoid, and also it's not very nice to have IPv4 tunnel overhead. So probably I wouldn't say that is the real solution. It's a kind of solution, but.
Last comment, and then for the overhead, I think we heard the same thing with IPv4. So that is the overhead of IP. And for example, in IPv4, one of the way of deploying really large-scale IPsec network is by encapsulating, to basically encapsulating your packet, your original packet in GRE. So kind of IP in IP, and then protect your GRE tunnel with IPsec. So you have the same issue, and that's if you want security today, I don't think you have many different ways of, if you want to protect your tunnel, I don't think you have other ways as secure as IPsec. So I agree that that is an overhead, that it brings overhead, but if you really need to secure and encrypt this tunnel, I don't think it would matter. It's always like always in security, that's always a trade-off, right? But so thanks for your attention.
Thank you, Eric. So we've heard how to facilitate the networks. We've also heard how to secure the networks. So I guess now we need to just run some applications over the networks, which leads us nicely into the next, and our final presentation for today. The presentation from Thomas Schmidt from FHTW in Berlin, and he will be discussing about, roaming real-time applications.
Hello. Okay. Thank you for the nice introduction. So I guess I have to hurry a bit. Okay, I'm trying to introduce joint work with Matthias here on starting from a video conferencing view on mobile mobility and IPv6 networks. Whoops. Yeah. Many people believe that the future of conferencing, voice and video conferencing, will be in the IP network, and many people also, there's a fair chance, many people believe that video conferencing will be will become more popular once we have the IP infrastructure around. When we're talking about the conferencing infrastructure, we have several things to think about. One is we have to think about addressing. That leads us to IPv6, for instance, as we are many times. It also leads us to multicast. If we aim at serverless video conferencing, group conferencing, we need group addresses. And it also leads us to user addressing, to nomadic users going around, being able to conference, as this guy here. And this was a topic of a talk last year at the Turina. Today we will stick more with the fact that device moves, and conferencing device moves, or even a conferencing session moves. So we want to, like in the mobile IPv6 approach, we want to see video conferencing surviving motion. So what is the agenda? First, we want to have a look. This is not good. That one? Okay. First, we want to have a look at requirements from the real-time perspective we have using video conferencing over IP. And we want to have a short look at internet mobility in general, and then try to work along the real-time requirements in mobile IPv6, starting with a local handover, some way for improvement, some discussion on improvement, and finally looking at the mobile multicasting problem, which comes along with mobility. So, to give you some numbers. To have a good video conference or audio conference, you want to have latencies not quite exceeding 100 milliseconds. More importantly, you want to have the jitter low, let's say half of latencies. You want to have little packet loss, and as interruptions are around in mobile IPv6, just to give you an idea, 100 millisecond of interruption is about a spoken syllable, which is lost if you're of the network. And the typical scenario is that you're in a group communication, you're a multicast sender and you're a multicast receiver, because you and your partner or your partners are addressing multicast groups. So some example of a video conferencing which was developed in our house. Well, it's a so-called Davico video conferencing system. It has some nice properties. One is that it implements IPv6, so it speaks IPv6 and a user location scheme. It is a multicast multi-point conferencing system. Uses a highly efficient wavelet video codec and does application sharing, and it's just a software to download and use. Well, you need a webcam, but nothing else. So back to the mobility stuff. There are several approaches around for mobility, and this is just for giving some, just for completeness. There's of course the mobile IPv6, which has been talked about a lot earlier. It has the very nice feature of being stateless and being transparent. On the drawbacks, on the problem side, it has first of all performance issues and security issues, as we heard earlier. To bring it to a point, to my belief, it is the major point that once you do these binding updates, which was talked about, you need to ensure that you are the owner of your home address, and you have to somehow prove this. And this is, well, probably the major issue. There's a, I believe, not very well-known but very funny approach, nice approach, based on multicast, just on the use on multicast, where it's multicast-based IP mobility, where every mobile node has its own private multicast address, and since multicast routing is location independent, well, you can be mobile, well, the speed or the performance is then more or less derived from the vicinity argument that you're moving little steps. This also has some security problems, and it is not symmetric, since multicast routing is not symmetric. So you have a problem if your correspondent node is also mobile, and it doesn't work anymore. Then there's the mobile SCTP approach, which is a layer 4 approach, a transport layer approach. Well, it does stateful handovers where you have a double binding to your two networks. Well, this has first of all, it's a transport layer. It's different. It's a different layer, different problem, and it has well, the problem that many layer 2 protocols do not support this double connection like 802.11, and there still is no node discovery in mobile SCTP. Well, and then there's ZIP, which is application handover. The application needs to implement this handover, and it is also not seamless for transport. You have to do a re-invite and do a new connection, but it is around. Yeah, we are concerned with the mobile IPv6, and it was how it works is probably known. As a host, you move from your home network to the first foreign network. You register with your home agent, and once you move and with the correspondent node, and once you move to your second subnet, you have to do a readdressing and perform a binding update with home agent and correspondent node. So, what is the issue we are looking at is not so much security but performance, and the first step we looked at is the local handover performance. Local means the local to your subnet. So we did an experimental setup where correspondent nodes and home agents were all very close. They were all the subnets were hanging on one router. So distances were collapsed. We used 802.11 using inter-resist components, which is important because they behave differently depending on the manufacturer. As a mobile node, we used the Linux Mibble stack, which is, I believe, draft 19. It implements draft 19, as far as I remember. We removed the duplicate address detection from the mobile node in case you do a handover. This is draft conformal. As a router, we use a FreeBSD router and the router advertisement daemon, and we changed the intervals, of course, to look at performance, having the router advertise an average delay of 50 milliseconds. That means it's 20 router advertisements per second. This is about 0.5% of the network capacity of 802.11b. And still conformal to the draft. For probe, we use an UDP probe, which sends reflected triggered packets between mobile and correspondent node every 10 or 20 milliseconds, and we sniff at all events to analyze them. And here are some results. What we see is, well, there's actually 3 curves. Oops, this one is packet loss, and as you see it, when the handover occurs, packet loss goes up to 100% and comes eventually down statistically. And here's we could figure from the sniffers, we could figure out there's a layer 2 handoff delay resulting from the 802.11 handover, which is in our case about 40 milliseconds, 40 to 50 milliseconds. But there are some slower results in the literature. And then what you see here is the readdressing, the statistics of readdressing and doing a binding update, where binding updates usually only took 1 to 3 milliseconds, and typically the readdressing altogether was about below 10 to, let's say, 50, 60 milliseconds. It's a statistical thing because binding router advertisements and all that stuff are statistically distributed. So the problem here, well, more than 90% of the events remain below 100 milliseconds, which is fine. But effectively, this is learning the handover from a router advertisement is terribly ineffective. And well, the problem is, well, the good thing is you know the handoff from layer 2. The bad thing is there's no standard to learn it from layer 2. But I mean, it is, well, this should be a matter of implementation. And once this is a theoretical curve. Once you learn the layer 2 handoff from your own stack as a mobile node, you then may reduce these router solicitation and router advertisement delay times to a reasonable value, let's say 1 to 3 milliseconds, and then you're fine. Then your IP reconfiguration, your local IP, mobile IP reconfiguration is the order of 5 milliseconds. That is quite nice. Just to give you an impression on these numbers, the clock tick of 802.11 approximately allows 10 router advertisements per second. So you're sort of more than 1 order of magnitude away from. And as it is a solicited router advertisement, it only occurs when your handover occurs. Well, actually, there is a stack implementing layer 2 trigger switches in old Windows 2000 stack, Microsoft Research, and the results are not really what you want to see. You see a scale of seconds here, and well, usually the handover takes 2 to 4 seconds, and this is just implementation noise. I mean, the stack is not really usable, and we at least couldn't fix it. But we believe there will be stacks around who implement layer 2 triggers, and then the problem will be essentially solved. There shouldn't be a performance problem from at least our point of view in local layer 2 handoff. But this, of course, is not the whole story, because usually the home agent and the correspondent node are in distance. You don't have them next to you. They may be in the US or somewhere quite far away. So you have to look, if you look at the problem in general, you have to consider your local, as your total handoff time. You have to consider the local time we were discussing earlier, and the time you need for the binding update to the home agent, and the time you need for the binding update of the correspondent node. And then you can sort of do some calculations, do some approximations, which is not terribly important. It's in the paper, but what comes out essentially is that the round trip time to the correspondent node and the round trip time to the home agent are the dominant the dominant timers here, and you have a 3/2 factor, which essentially comes from the return routability procedure. It would be the prefactor would be less if the return routability wasn't present. Well, there has been a lot of fuss about this return routability and the poor performance because it goes back and forth and back. Well, what we believe is, the factor is here, but the problem is independent of return routability. The factor could be, for instance, reduced, or the procedure could be reduced by what is a new attempt as using cryptographically generated addresses or something. But as long as your procedure depends on these return round-trip times to the corresponding node and to the home agent, they just, the handoff time just extends with your distance, whatever you do. I mean, and then the factor is not so important. It's more or less the dependence. Also from the jitter, it's a similar arguments. You get something as an enhancement factor which depends on the relation between round trip time to correspondent node and home agent, and what actually we want to look at, and what one wants to do is to eliminate the dependence on the distance to the home agent and to the correspondent node. Well, otherwise, it is just, in real-time applications, mobile IPv6 is just useful in local environments. We don't expect to become round-trip times between Europe and the US to be in the order of 5 to 10 milliseconds. So, there are several attempts to do mobility faster, to speed up mobile IPv6. One is the hierarchical MIP draft, which is a draft in some iteration. It relays on proxying the home agent in regional domains. It is, they're called MAP, mobility anchor points, but it's essentially a home agent proxy. It's basically the only thing you can proxy, because a correspondent node you can't proxy. You're talking with it. And, well, the good thing is the map is local to you, and the map update is a local problem. And if you're moving within your map domain, you're fine. You're only updating your map, and as all your traffic, all your speech is going through the map, with this HAMIP approach, as all your speech is going through the map to the correspondent node, using a so-called regional k-off address, which is local to the map, all local movement is hidden. That's fine. So you can have a handover just on local terms, and you will be fast. Once you move from one map domain to the other, you have this essentially the same problem as you had with a mobile IPv6 approach. You do need to perform a binding update to the correspondent node and to the home agent, because you get a new regional k-off address. The regional k-off address is local to the map, to the actual map. Well, and by this, you have made the dependence on your round trip times to the distant nodes less likely, but still it is still there. You do need to update correspondent node and home agent directly. Another approach is what is so-called the fast handover in mobile IPv6. This is essentially a technique for hiding, not for proxying, but for hiding the handover. And the attempt works this way. You anticipate the handover by layer 2 information, which is layer 2 dependent. And once you know you will move, you look at, well, which is part of the information you need on a map saying, okay, your new access point belongs to this router. there need to be a topology map of layer 2, layer 3 information. And once you know which is your new router, you do binding updates and all that stuff in advance, address configuration and so on. And this eventually leads to a handover hiding, or hiding distant handover durations. It has, to our understanding, two problems. First, the layer 2, layer 3 topology is not present to my knowledge. It needs to be acquired somehow, and it is quite difficult to know the whole layer 2 and whole layer 3 and the matching of all topologies. And the second is a more principal problem. It is, at least in common techniques like 802.11, it is not really predictable what will be your exact moment of handover. This is, well, basically it also depends on the movement of the device. And if I'm going irregularly, it may look that I continue in a handover direction, but then go to the other way. And so there might be this, or it's likely to have this situation that a handover is prepared but does not happen. With the fact that if you anticipate the handover, you may redirect all your traffic but still do not perform the handover, and then you're in trouble. You've lost all your packets, even though you didn't even, there was no reason. Yeah, and well, we thought about it, and what is our conclusions from that? If one wants to improve handover performance, the first wisdom we learned is that you cannot do without a proxy agent. Also, the FastMap proposal also has a proxy agent. You need a local anchor point. Well, what we would suggest then is use the hierarchical MIP proposal, because it's quite okay, straightforward. The second is that won't do all. You need to do handover hiding techniques as well. And well, what we would propose is do it differently. Turn your sight and don't anticipate the handover, but look at the back and use the previously established path. Once you've performed a handover, try to continue speaking along the old established path, which relates in the HMIP environment to the previous map. So what you do is you do a binding update to the previous map once you moved, and have it forward packets as well as have it forward your packets. Continue speaking through the old path. That exactly means that you're off the network for local handover. Well, you do it as long as your binding updates with real correspondent nodes and home agents are not completed. And there's a slight problem, because from the MIP draft, the correspondent node, in this case, needs a time where it has two binding cache entries for your communication, and it needs to preserve the last, which is not conformal with the MIP draft now, but it's an easy or simple extension. One should note that it also covers rapid movement. If you're moving very rapidly from one anchor point to the next, you can preserve the last stable, which is also a problem. Yeah, there's some side note on tunneling. I mean, the HMIP approach heavily relies on tunneling. Tunneling is not really a loved thing. You have an extra overhead. You may have fragmentation if your traffic enters a tunnel, and you may lose your quality of service parameters. And well, there is, at least in the mobility in packets carrying mobility header extensions, the option, or there is the situation that your source and or destination address are hidden in routing headers or home address option headers, as was just discussed earlier from the security point of view, and those addresses enter the pseudo header, so that you have no real problem in readdressing forwarded packets. You don't have to recalculate checksums and so to our feeling, most of the packets are mobility header extended packets. One should think of just forwarding and readdressing them by the maps, by the local anchor points. Those maps have, a mobile node does have a security association or a secured relation to the maps. Of course, you can't exactly do it without these mobility header extensions. So, last point is the mobile multicasting. The problem I mentioned in the beginning is we use, from the video conferencing point of view, we need both. We need a multicast listener and we need a multicast source mechanism. Problem, well, the problem is asymmetric, and the problem is that multicast is of slow convergence, and here are some numbers, which is, I don't know, which may be much less in some cases. For instance, if this 30 seconds comes from the MLD timeout, somehow, if you have a layer 2 triggered group join, it may be faster, and also the building up of a routing tree, of a source tree in multicast may be quicker than 3 minutes, depending on the routing protocol. Maybe in PIM-SM, if you have a stable fixed rendezvous point and no shortcuts, it may be much quicker, but still it is slow. It is slower, much slower than some milliseconds. I mean, so, yeah. What we try to use, or what we use for thinking of multicast is, first, that multicast is stateless and unreliable. So just this sort of communication. And the second point is, well, it would be nice if there is no extra multicast infrastructure, if the multicasting proceeds through the normal unicast infrastructure. So let's see first at the listener side. You have the multicast listener in this HMIP approach, which is anchored at a map. It has a fixed anchor point, and what it should, from our point of view, do is submit this MLD listener report through the map, as all traffic goes through the map, and the map, or the new map after handover, then will record, or should record, the group membership in the binding cache. It should know that a certain mobile node is member of the binding cache. Once it knows this, it can answer MLD queries, or if it is a multicast router, keep the group. And once this is done, the map can forward multicast packets as unicasts to this mobile node. It is taken care of. Once at the time of a handoff, which is a more interesting one, you have exactly the same situation as in the unicast case. You have to, well, you go to a new map, send your listener report again, but then you have a long off time. What you try to do, or what you do, is you send a binding update to your previous map, receive your packets from the previous map, and have it forward the packet until you receive multicast packets from your new map, and then you can, by sending a binding update with 0 lifetime or so, you can stop the forwarding. So the more difficult point is the mobile multicast source proposal. First thing is, if you're sending multicast packets, you need to consider that your application usually is aware of your source address. This was discussed in the video conferencing, and you have a problem if you do not keep your source address. This is, well, we believe in contradiction to the MIP proposal that you need to use home address option to have the multicast source address being to stabilize it. Well, what then? You send. Well, the multicast routing tree is started once you start sending multicast packets. And what you do is you just send them. Your tree is erected, and at the crucial time of the handover, you start sending twice, in the new map domain and via the old map domain. The old map domain usually has an established routing tree, so your communication is preserved, and the new map domain will start to build up a multicast tree. Here's one problem: you don't know when the routing tree is erected, so you have to. Well, our suggestion is to have a timeout depending on the protocol. Yeah. This also should work on rapid movement, as you can stay with the established map. I have some pictures here. This is the first situation. You are just sending your multicast traffic in a map domain. You have a local handover, which is transparent, as always in HMAP. You have the handover here, and you establish a bidirectional stream, and once your timeout is arrived, you stop sending via the old stream. Whoops. So this was this is almost my last slide. What I was talking about is the measurements on MIPv6 and how it can be done suitable for real-time communication. One of our conclusions is that proxying and handover hiding techniques are sort of inevitable if you want to meet these real-time requirements. And there's an approach presented on multicast, and what we will do in future. This is all theory now, is to analyze and simulate it, and hopefully refine and optimize it. And maybe there's still some mistakes in it. So for the last slides, once you're in an important video conferencing, you don't want to be disrupted. You don't want to be disturbed, and this is especially true if it is an important partner. And thank you. And questions.
Okay. If there are no questions, then I'd like to thank Thomas once again. This brings us to the end of the 6net workshop, and we hope it's given you a bit of an insight into what 6net is doing, the type of things that we're working on, and hopefully we'll give you an overview of IPv6 in general. Coffee is waiting, so we don't want to keep you too long. But I would mention that all the presentations from today will be made available online on the 6net website. I will put these on in the next day. The URL is www.6net.org. It's quite short and quite easy to remember. And I'll put a link on the front page. And then finally, I would just like to thank firstly all the presenters who have given talks today. And I'd also like to thank the technical crew at the back who organised a very good video conference today with Jordi Palet in Madrid, which I think worked very well. So thank you for that. And with that, I will close the workshop. Thank you.